Alright, so we're just going to talk about how you look at different functions and look at the patterns of their graphs. And so some of these are going to be really familiar from algebra class, especially these ones, lines and quadratics. You spend a lot of time looking at them. But what really comes out is we want to make sure that we understand how to find the various pieces that we need, so the slope and the y-intercept for these, our coefficients a, b, and c, if we have that. We have about vertex form. So we'll take a step to look at those, and then we'll also look at some patterns that you might not be as familiar with. Right. So for this one, again, we have it's a quadratic. It's this parabola shape. That's our parent graph, x squared, and then we can shift things around. So we have a translation to the right, so that h value, if h is greater than 0, moves our vertex, the whole graph, to the right. And then we can stretch it and add some value k. So we can take this graph and we can shift it up or down. So we can move left to right, up or down. That moves it over, h, and that moves it up k. And then we can stretch it by a factor of a. That's our dilation. So we can make it flatter, we can make it narrower, depending on that value of a. And then if we make a negative, we have all the same properties except that it's flipped over and it will look down, it'll be concave down as we go forward. Right. We also have another type of function that you're probably not as familiar with, which is called our power function. And the key here is that x is our variable, just like always. And so b is a power, but we have x to some constant power. The power is not changing. And if we were to look at the graphs and look at some of the pieces, we'd see kind of this shape down here that looks almost kind of like half a parabola as we go through it, except for when we get over here, and we can see that that is not going to come back up. So it's not a parabola, it's a different shape as we move forward. And so, again, the variable is the base. That's a key idea. We want to make sure, because we're going to have a different one in exponential where the variable is the exponent. And then we have our different pieces where we have some restrictions on x, where x is non-negative, and we'll talk about why down the road that has to be a restriction. And if you think about it, you could graph these things, right? If you had a negative value for x, would be no problem, especially with something like this, 1/4 x squared. This is just a parabola, so this other half does exist, right? But we have a restriction on this, right? So it's a restriction to just be our positive. So our domain is only our positive x values. If we look at the other one, we could graph these things. This would have x to the 2/3 power. If we put in negative values, we'd have x value, or x to the 1/3. This would actually come down and dip like this. This has a sharp point, which is a problem with functions when you get to something like calculus. But it does exist. It is there. We simplify it to look at just our positive values. Same thing again. This is a rational function where we'd have another piece that would be over there. So the other part exists. We just have a restriction on the domain that we use. Our last one is called a power. An exponential, and this is where our exponent is in the our exponent. So the x is an exponent, and that's what varies. A, b, and c are constants. We have restrictions on a, b, and c, where we kind of look at what we have with those in terms of different shapes. We do have an asymptote in this one, and so you just think about it as a vertical shift. And so if you were to look at the parent function, so this one up here, where we have a times ab to the x power, as x gets really, really big or x gets really, really negative, we can talk about what those values will approach. And so if we look at it, if we take a very large value, let's say that b is greater than 1, so this case down here, let's just say 2. If you take 2 to a giant power, you get a giant number. And so this would be very large. And if we take a negative value, remember that's just a reciprocal. So it would be 1/2 to a large power, which is close to 0. So that's why that asymptote in the back exists. And we also have a large value as we increase there. And if you flip things with a negative sign, it will become different. But again, we'll play around with values and see what we have. Okay. So if we're trying to look for these, so let's just say we've given data. So this is a difference in that we don't have an equation, we have data, and we're trying to fit the appropriate function to the data. That's our overall goal here. And so if we look at this, this is a constant difference of 3, and then this is a constant difference of 2. And so this is going to be a linear function. This is our just kind of rise and run values as we were to go through this. And if it's constant all the way through, it's going to be a line. And that should be pretty straightforward and makes sense to you. So if those are constants, then again, not the same value. It doesn't have to be -3 and -3, but just between values, it's the same. We would get a line as we move forward. If we were to have a constant difference on one side, so we add 3 over here, we can see that's not the same over here. So when I add 3 over here, I don't add a value over here. I can see that I went from 2.25 to 4.5, right, which is 2.25 difference, and then this is already 4.5 difference, and this is a 9 difference. So this is a multiplication of 2. So when I have an add multiply property, that is going to be an exponential function. If you looked at an equation to start with, right, and you had 0 and 1, and you added 1 to both, you'd already see that you've doubled. So you had a constant difference of 1, and then you've doubled. Well, this looks like a constant difference of 1 too. But if you do another one, right, this is now 4. So what you're doing again is you're adding 1 on this side, and then you're multiplying by 2 on that side. And that's where you get the add multiply value as you go forward. So that's going to be our general form for an exponential. Now, if we look at those values, how we would find it, right? So I would take a point, it doesn't really matter, and then I would solve for my pieces. And so I took this first set up here, that's my x value, and that's my y value, in that case f of x. Then I just plug stuff in, and I try to figure out what I got. So I get c pretty quickly with that 0 value of 1.25. And then I'd take another point, and I'd plug in with my value of c, and I would get an equation with just a and b in it. And then since I have 2 variables, I need another equation, so I get another equation. Doesn't matter what I pick. And then I would get another value with a and b in it, and now I can substitute. So I could solve for a, and I could figure out b, or vice versa, and then once I have a or b, I can figure out the whole thing and get my equation. It doesn't work out very well with these values, so we'll leave it there, but that's our process as we move forward. Alright, so we have a multiply property. So if I multiply by 2, and then I multiply by another constant, again, it doesn't have to be the same, but that's by 4, this is going to be my power function. It's a similar method to exponential, right? If you were to take your general power function and you were to take your data points and plug them in, again, since you have 4 variables here, you're going to need 4 equations, and you're going to have to work through and solve it. Now you can guess a little bit and hope that you just have a value of A and a value for B, that you don't have C and D where things have been shifted around. And you can look at the graph to kind of get a sense of that. But if you do that, it'll be hopefully pretty straightforward. So this is our equation. We would solve it, but we'd have where C and D would drop out to be 0. And then the last one, the quadratic, doesn't have a really simple pattern. It has a constant second order difference. So what that means is if we take a difference here, that seems pretty straightforward. We just added 2. And then we look over here, I'm adding something, but it's not the same. It's not multiplying by a value. But if I take a difference of the differences, I get a constant value. And so that means that it's going to be a quadratic function, and we can fit things to a quadratic. And again, we take our ax squared plus bx plus c, and we'd have to get 3 equations in that sense to solve it as we're moving forward, because we have 3 variables. Right, so that's our second order, and that would make it a quadratic.